Today we are going to perform a Nastran Solution 200 tutorial. This one's going to focus on topometry optimization. My name is Christian and I'll be doing today's tutorial. So what is our goal by today? Here's same as before. We want to minimize the weight of some structure. We want to have some sort of displacement or stress constraint. But the main goal of this example is to show you really what topometry optimization is. Often you hear topometry optimization described as an element by element optimization procedure. This could be sort of confusing at first, like it was for me, but hopefully by the end of the video you understand it a little bit more. Here to start off with, let's go over what the different, or really what element by element optimization is. Here you can see that we have some plate with some thickness. So here let's go ahead and switch to the pen. So here let's suppose that each element is driven by a single value T for thickness. With element by element optimization or topometry optimization, it's going to split the thickness. It's going to give each element its own value for thickness. So here T1, T2, T3, and so on and so on. Before, with size optimization, only one parameter would be controlled. This one parameter would drive the thickness of each element. But with topometry optimization, it's element by element. So that one parameter is then split. So then each element has its own parameter for thickness, for Young's modulus, whatever parameter set as a design variable. So by the end of a topometry optimization, each element will have its own value for, say, the thickness or any other parameter that's set as a design variable. Here's what I'm going to cover. A quick comment regarding the structural model. It's always useful to know how the model is loaded, what load cases are there, where are the supports. Then I'm going to cover probably one of the most important things in this video, the optimization problem statement. This is the first step before you can set anything up for Nastran Solution 200. This problem statement is composed of the design region, the objective, and the constraints. Of course, we are going to perform the optimization and then view the results afterward. As always, if you're an engineer, if you're starting off with optimization, or if you're performing a more advanced type of optimization and you require someone to provide guidance or training, I am more than happy to help you address any challenge. So here's my email address, and of course I only take inquiries regarding Nastran Solution 200. This is my specialty. Also, if you're a student and you want to learn how to perform optimization, this goes for engineers too. You can get access to the Nastran Solution 200 web app by also contacting me at this email address. Now, quick comment regarding the structural model. One end is fixed, so here the familiar diagonal lines are fixed. Here you might be wondering why my straight lines are not straight. That's because I'm using a mouse. Here at the other end, we are applying a transverse load. Now, what about our optimization problem statement? This again is composed of three items: your design region, your design objective, and your design constraints. Here, we're going to say that our design region / variables is thickness. Right now, there's only one thickness, and this is used to drive the entire thickness of each element. So right now, we only have one thickness if you're performing size optimization. Again, with topometry optimization, from that one thickness, it's going to give each element its own thickness automatically. So T1, T2, and T3. And then here we're going to have T4. And it's going to vary each thickness on an element by element basis. Here, just a quick comment, we're going to apply some constraints and an objective. Here the objective is to minimize the weight. Our constraints, we want the von Mises stress for both the top and the bottom fibers to be less than what do I have here? 250 megapascals. And here, let me just double check the units just to make sure I'm using the correct units. So 250 megapascals for the upper bound of the von Mises stress constraint. And as for displacements, we're going to say that, here, where's my pen here? That for nodes 14, 28, 42, and 56, we're going to say that the downward deflection should be no greater than 0.01. So let's go ahead and get started. Here is basically a repeat of what I said a moment ago. Actually, let me take time to show you a different example. So here's an excellent example. Let me see if I can zoom in. So here, when you first enter the homepage, there are these introduction icons. These are meant to represent the different optimization types available through the web app. These will actually be helpful in the following discussion. So let me go ahead and paste that here and write some notes on this. So the first icon is for size optimization. Here you can imagine that if this was actually composed of 3 elements. So here I'm just drawing lines to represent the boundaries of the element. And if we vary the parameter height, so here let's go ahead and write the distance from the top to the bottom of this beam will be represented by an H design variable. When we use size optimization and vary the height, it is going to vary one height for each element. With topometry optimization, here we have 4 elements. It's going to assign each element a height of its own. So here H2, H3, and H4. Here there's tapering. So here, just to make it simple, I'm just assuming there's only one height. So it's going to go ahead and vary the height for each element by itself. Here, the plate, another example. Before, we just had one thickness that was varied. Here you can see how much thicker it is before compared to after. But with topometry optimization, it gives each element its own design variable. So here T1, T2, T3. And then by the end of the topometry exercise, you can see that each element is different in terms of design variables. So this is the main difference between size and topometry optimization. Let's go ahead and now talk about what steps are necessary to use Nastran Solution 200. So the starting BDF file, of course, this procedure can be done with any example that you may have. Here, I've already taken time to construct my cantilevered beam. Let's go ahead and quickly plot some of the constraints here, just so you know that it's fixed on one end and there is a transverse load on the other end. When you export this model, it's going to be contained in a BDF file. So let's go ahead and get that BDF file actually. If you go to the home page of the web app and you go to user's guide, there's a list of tutorials. The one we want is the one called Topometry Optimization of a Cantilever Plate. If you download this BDF file, this BDF file contains the same finite element model as the one you see here on your desktop. So that would be this file here. So this is our starting point. You'll notice that this file is currently set to solution 101. We have to convert this to a Nastran Solution 200 BDF file. So now what happens after we have this BDF file? We have to go through this process of converting it to solution 200. We have to specify in Nastran terms what the design regions, the objective, and the constraints are. This is actually pretty simple. We'll then perform the optimization and view the results afterward. So now let's go ahead and switch over to the web app. This web app again lets you convert an existing solution 100 BDF file and convert it to solution 200. If you want access to this web app is available to both students and engineers. Feel free to contact me at this email address at the bottom of the PowerPoint slide, and I will get back to you. So let's go back to the home page of the web app. And here in the far right hand corner, we'll click on the topometry icon. We'll go ahead and upload this PDF file. It's going to first define all the properties that we can set as design variables. Here, for example, if we wanted to set the Young's modulus as a design variable, it's going to split it for each element. So then each element will have its own elastic modulus that will be designed. We could do the same for Poisson ratio, for density, and for any other parameters that are shown in the list. But here I want to set the thickness of P shell 1. And here we're going to leave the bounds as is. We'll go ahead and move over to the objective, and here we'll go ahead and click on the weight. You'll notice that here I have the 3 critical pieces from our optimization problem statement: the variables, the objective. We just created the weight to minimize the weight. There's our objective. Let's move on to the constraints. Here I have a big list of quantities I can set as design variables, and you can see there are quite a lot of them. Here I can set the stress as a quantity I want to constrain. Next, we have to specify what type of stress. Here we're going to apply this to any element associated with P shell, and then we are going to specify this for the von Mises stress of the bottom fiber, and this is going to be anything, or rather P shell 1. So any element associated to P shell 1 will have this von Mises stress constraint applied. And for the upper bound, we're going to leave it at 200 E6 pascals. Let's go ahead and create a displacement constraint. Go ahead and click the plus icon for displacement. We'll say we want to measure this in the Z direction, so this would be the T3 component. And here we want to do this for all the nodes at the end of the cantilever beam, so that would be here where the load is applied. Here I already looked at the ID numbers, and I know that they are 14, 28, 42, and 56. So here, these are for nodes 14, 28, 42, and 56. I want to make sure that the lower bound is 0.01. So here we're saying that the Z component of deflection should be no greater than 0.01. Let's go ahead and go back to the web app, and I think at this point we can go ahead and just jump right over to the exporter. We'll go ahead and click on option 1 to download this new package. We'll extract this package, and inside of this new folder we'll go ahead and double click start MSC Nastran to start the optimization. A quick comment regarding some of the files that are in here. The model is the converted version of this PDF file, the original one. So before it says solution 101. If we open up this new file, you'll notice that it now says solution 200. And there's some additional statements for optimization. In addition, the second file, design model, has all the Nastran statements for the design region, the objective, and your stress constraints. Once the optimization is complete, it will be reported in this new web page that you see here on the screen. The first thing to look at is the final message. It says run terminated due to hard convergence. The green checkbox indicates that is a success. Here we see the weight went from 19.5 units of mass to 3.966 units of mass. So here we can see that the optimization was successful. The second thing you should watch out for is the normalized constraints. Usually you want to have a final constraint value less than 0.005. Anything greater than 0.005 means you have a violated constraint, but anything less than that means you've satisfied your constraints. So here you see that the initial design has the normalized constraint of 18.50407. So there's a constraint that's grossly violated. If you want to know which constraint this is, you can go to the results section, click on responses, click select files, and then track the F06 file and upload it. And then click on maximum constraint for each design cycle. And then here, I don't think it's available here. Let me go ahead and check if it's in here at all. I just remembered that by default, the constraint values are not included in the F06 file. So here, just be conscious of the fact that the normalized constraint is way over 0.005. So at the beginning, the first design cycle, there is a violated constraint. Here, the next design cycle is still positive 6, so it's still violated. By around the 5th design cycle, not even there, by the 6th design cycle, you finally have a normalized constraint less than 0.005. So at this point, you have a solution that's actually satisfied. So now with this, let's go ahead and discuss how to view your results in your post-processor. Now, given all the parameters that could be set as design variables, a Young's modulus, a Poisson ratio, and as a density, the following is my method of seeing the new values. So let's go ahead and go through that process. So here is my original file. I'm going to create a new file here called new version. I'm going to make a copy of this one in here. Remember, before the thickness was shared by all the elements, that's because we use a P shell with an identification of 1 to specify the thickness of 0.00 or 0.01 rather. In the folder where the optimization was performed is a punch file. This punch file includes new P shell entries. So here you can see that P shell identification number. This P shell has a different thickness from this one. This one has a different thickness, and so on and so on. So what you can do is move this file from the left and to the right. You also have to keep in mind that you have to update the element numbers. And here, just bear with me while I check to see if this has already been done for me. And let's go ahead and see what the final result look like. So here on the right, you can see I've already copied over the P shell entries. The other thing you have to make sure is that your elements then use those new element ID numbers. So here everything looks good. Maybe this one would be the one worth moving here. So let's go ahead and move this here. So just a quick summary regarding what I just said. I've already taken time to merge the punch file and the BDF file. So here what we can do is just open Patran, import this new version of the BDF file, and then we'll go ahead and display the thickness distribution. So here, let me import this new updated version. So here it is. We'll go ahead and go to display shell thickness, and we'll go ahead and select all of these elements here. And one other thing I should do, so here we go. It's very subtle, but you can see that now each element has its own thickness associated with it. Before it was one continuous thickness. Here it would be worth me doing the same thing. Let's go ahead and show the thickness for everything. And here we go. So here you can see the thickness was actually a little higher before. And here in the end, you can see how it's gone ahead and varied the thickness of each element. So there you have it. That's how you perform a topometry optimization. Remember, it's an element by element size optimization, if you will. There's nothing more to it. I believe that was the last comment I wanted to leave you off with. As a reminder, if you're an engineer, if you want to perform topometry optimization or some other type of optimization with Nastran, feel free to contact me at this email address. If you're a student or an engineer and you want access to the web app that helps you set up optimization, you can also contact me at this email address and I will get back to you. With that, thank you so much for watching, and I'll stop there.